Structural Analysis of 3-Axis CNC Machine, Episode 2. And today we will have a look at the load on our x-axis, that one, caused by y forces on our tool. There it is, my spindle. Yeah, the little guy is quite handy for showing such things. And I will completely skip the intro and the basics and dive right in. So yeah, it would be best if you watch the quite lengthy hour-long part 1, link down below. So forces on the y-axis on the tool. So again, we can simply watch our CNC machine from the side with the z-axis and the y-axis. And it's basically the same picture as last time. Yep, maybe you remember, or maybe you have to review the video. I hope not. It was quite long. But we have here the lower X bearings and the upper X bearings. And we have our two dimensions, which were important back then. The distance between our upper and lower X bearings on the z-axis, that's zx. And the distance between our bearings and the spindle axis on the y-axis. So y tool, x spindle, tx, y tx. And our forces will now be on the tool, which is somewhere down here. And therefore we need a third dimension. And the third dimension is on the z-axis from our tool to, in this case, the lower X bearings. So from tool to our X bearings. And our forces, we said, come from the side on the y-axis. So let's draw that in. I do it 5 centimeters long, and this is our force. So that's all we need, I hope, to calculate it. As before, I've done it for the forces on the z-axis. I put that into some software for statics calculations, and this time I entered the data correctly, so I don't have to turn it awkwardly. Again, we have our X bearings, these are here, and our tool would be here, and our force to the tool don't have a much, oh, is here. And this is, I entered, I guess, 1 Newton. It doesn't really matter if it's 1 Newton or 1 kilonewton or 500 newtons. The result that is in relation to the input force will be the same. So if we get put newtons in here, we will get newtons out on our bearings. If you put a kilonewton in here, we get some fraction of kilonewtons out on our bearings. How the forces are related is completely dependent on the geometry. That's the nice thing about statics. So I put that model into the software, let it calculate, and it gives me some forces exerted by the bearings. And it says for F1, that's 1, 3. Yeah, I almost diddled over the number. 1, 3. So on the x-axis it says 0.5. So just let me cross-check. So this would be something like 2.5 centimeters force in this direction. And on the x-axis for the lower part it says minus 1.5, and sorry, got it wrong. Plus is in the other direction. If you draw it as an arrow. And down here we have minus 1.5. Yeah, now the arrow is coming from the left. Minus 1.5, so 7.5 centimeters if our initial force, 1 Newton, is 5 centimeters. So the software says 7.5 centimeters here. That's quite a lot, isn't it? So this is 1.5 Newton. This is, sorry, English, 0.5 newtons. For English viewers, I make a dot. And then we have two more components on the y-axis. And I will use another color for them because they are a little bit eerie. This is force of plus, so this one, and only a quarter, so 1.25, something like that. 0.25 roughly. 0.25 Newton. And down here we have roughly minus, so in the other direction, minus 1.25 Newton. That's interesting. Yeah, I mean, we have a force here, so we would expect to have some other forces in you know, on the same axis, on our y-axis. But why the hell? Where is that coming from? Well, we'll see. So, back to our little model of the machine. And we basically do the same as we've done last time with the momentum approach. So we simply say the whole thing is rotating about the center between our two bearings. So yeah, simply for ease of drawing, and as I mentioned in the other clip, you can choose this point arbitrarily. It will yield the same result, but if you choose it wisely, you have a little less work to do. So our force is coming here from the side, and so it tries to rotate the whole thing around that point. And the lever, in our case here, the force will attack here. Our lever is basically that ZTX, so the distance on the Z-axis between the tool and our lower bearing. ZTX plus half of the distance on the Z-axis between our upper and lower bearing. So ZX half of it, ZX over 2. Yeah, multiplied by our force. Remember, momentum is simply the lever you have around the point of rotation times the force, and it tries to rotate the whole thing this way around, and this will be our momentum. So our momentum is F times ZTX plus ZX over 2. Simple enough. Now we have to counter this momentum in the opposite direction. So we want to create take another color, a counter momentum this way around. And to do that, we will need two forces, up here and up here. This one pushing in this direction. So, without saying how long it will be, and up here pushing in this direction, just so we know where our forces are. And this should be the same momentum. And yeah, I call these forces F momentum, just so it looks a little bit more professional. So F momentum, and the length of our lever is ZX half. Yeah, one lever pressing here, the other lever, force is coming from here, and yeah, we have this 2 times. Times 2, and yeah, we can forget about that, and this should be basically the same. So a little bit algebra. I put the Fm equals F times, and now I divide the inside of the whole thing by the Zx. So that Tx divided by Zx plus Zx divided by 2 Zx, and this is simply, yeah, Zx divided by 2 Zx. This is simply 1/2. Ooh, now we have to calculate that. Let's see if we can do that without calculator. And that was obviously bullshit. So our ZTX is 1/2 over, sorry, Zx, which was 1, plus 1/2. So, and you can see this is simply 1. That's the reason why I've drawn exactly that dimensions. So that's basically 1. So our momentum here, or counter forces, are for the momentum are exactly the same as our attacking force here. So in our scale, 5 centimeters. And it's easy. Don't worry, I have a nicer picture for the summary. And it's easy to see. I mean, we're basically turning in one direction with a lever which is of the length 1, so ZTX plus half ZX, and we turning into the other side with 2 levers which have exactly half the size, ZX half. So these forces have to be, at least for these dimensions, to be exactly the same as that force. That's quite nice, but something is missing. If you sum up all forces on the y-axis, you see that we now have an excess of 5 centimeters or 1. So this force on the y-axis would be cancelled out by that force, but this force is left over, and the whole thing would be, well, equilibrium of forces would move in, or would be accelerated in that direction. So we have to draw in some counterforces, and I'm using blue to do that. So how big would be our counterforces? So basically this is the same at that force, this is the same at that force, and we need to counter one time that force. So our, and I call that F force, would be, we apply 2 times, once up here and once down here, is our force halved. And the reason why the counter force for that on the upper bearing and the lower bearing has to be exactly the same. If they would not be the same, we would add another momentum, because then we had here additional forces on the lever, which which if they would be different would push again in one direction or the other. So they have to be exactly the same. So counter force 25 centimeters here, F, and 2.5 centimeters additional here. Now I hope you remember the thing with the force triangle, adding up and neutralizing forces. Let's say, so I have a force here and a force here, and then I simply close up the triangle with the resulting force. This is just a special case of the force triangle, where basically our angles are 0. That is, our upper angle is 180 degrees. So it's all flat in a plane. So I have this force here and another force there, and the resulting force is then simply the sum. Yeah, no trigonometry or drawing with my triangle ruler required. So our resulting force here would be, they go in the same direction, the sum of both, and since we want not to calculate the force exerted by the bearing, but the force exerted on the bearing, we have to change the direction. So the force is coming with 7.5 centimeters from here. And this is simply the F momentum, which we already calculated, plus our F. Yeah, I know. But up here, the forces are opposing each other. So they partially cancel each other out. So to draw it a little bit easier, you can say, okay, this is my initial force, then I have another force going that direction, and so the resulting force is the rest. Should be clear. I said I want to keep it short. So basically we have 5 centimeters here, or 1, and 2.5 centimeters here. That was, where have I calculated, half. So we have a resulting force from this direction. Yeah, 2.5 exerted by the bearing and 2.5 exerted on the bearing. So yeah, that would be here. That would be our total force. That direction, and that is Fm minus Ff. Let's have a look at what our software calculated, if I can find it. The sheet is over here. Yeah, 0.5 newtons. Yeah, so 0.5, or in our drawing here 2.5 centimeters, that direction, and 1.5 newtons, so in our scale 7.5 centimeters in that direction. That looks good, but we still have these then quarter newtons that seem to push on our bearings. And let me think about that. Yeah, I guess it's again, you remember we got quite odd numbers for our forces on the z-axis too, and the way this software works, it actually allows to be the our rods. There's a better name for that in English. Our connections to be stretched and to be compressed. So they have, in that model, software uses, they have some elasticity. And if I look at that and say that's a fixed point, and I press here, I basically put some strain on that connection, and I lengthen it. And if I lengthen this connection, I put pulling forces on these connections. And if I pull here, I'm contracting, shortening this connection. And therefore we have these odd numbers here that say, okay, our two bearings are compressed from the top and the bottom. Yeah, well, but it's free software, don't complain. By the way, link down below, but it is in, as you can see, in German. I don't think they have a English version. I'm sorry. Use Google Translate. Yeah. So, results. I have here the nice drawing of the whole thing. Yeah, it's basically the same. We have the force here. Ignore for time being the dotted forces. We have our force on our tool on the y-axis. We have our dimensions, the distance from the tool to the lower bearing on the z-axis, the distance between our lower and upper bearing on the z-axis, and the distance from our tool to our bearings on the y-axis. And yeah, here it's drawn on the other way around. We have the force countering the momentum, which is 1/2 plus ZTX, so that length of lever over, ZTX, so that length of lever over that length. Yeah, we already calculated that. Then we have the other force, the blue force, and just the indexes say this is force on the x-axis caused to cancel out a force caused by tool y-axis, and this is Fxmty is a force on the x-axis to cancel out a momentum caused by tool y-force. Yeah, this series will have quite a few episodes, chapters. I mean, we have 3 axes, and for each axis we have 3 different directional forces we can calculate. There will be an Excel spreadsheet, and maybe I will make that available to the public. Anyway, so here momentum force and the force to cancel out, to cancel momentum force and so on, they add up, resulting in that larger force here on our bearing. On the other side, the force to cancel out the momentum and the force to cancel out our excess force on the y-axis, they are opposite, so we only have a smaller force here, the rest, so the momentum force minus the force. And down here, the dotted lines, like in the previous episode, how does the whole thing look when the force comes from the other side? And of course, it's an exact mirror image. So, and like last time, I get out the drawing of the CNC machine I plan to do, and we can have a look at the forces on, yeah, something not yet real, but hopefully soon to be. So I'm back with the drawing of my CNC machine. Still the same like last time, and we have between the centers of the upper and lower X bearing 118 millimeters. From our center of the X bearings to our spindle axis or tool axis, tool should be somewhere down here, 100 millimeter, and I just eyeballed it and said, okay, from our lower X bearing to our tool tip, 150 millimeters. And if I put that into our formula, then I get for the blue ones XFTY, which was simply half the force on the tool, our cutting force, I get 94 newtons, and my maximum cutting force I plan for this machine is 188 newtons here on the axis. And the force to counter the momentum, Fxmty, is 333 newtons. That was that formula. And yeah, I mean, it's always at least half of the cutting force, and then it's the distance between our bearing and the tooltip over the distance between our bearings. And well, in my machine that's not very favorable, so it's 150 over 118 plus ein 1.5, and yeah, I mean this is 333. And in result, for the lower bearing we have to add the two numbers and get to 427 newtons, and for the upper bearing we still have 239 newtons. Yeah, and then I looked into the data sheet for the SBR 10UU bearings I want to use. If I can find it, it's not here. Oh yeah, here it is. And for SBR 10UU it says maximum dynamic loading is 372. And if you watch the intro, I talked about that too and gave a link. Yeah, so my SBRs can take 372, and we have 427, and I was, yeah, a little bit shocked. But then I remembered, fortunately, we calculated the forces on the whole upper and the whole lower and the whole upper assembly. And upper and lower assembly will of course contain two bearings. So yeah, the load per bearing is only 213.5, and this is, at least in theory, doable. Yeah, and at that point I should admit another shortcut I've taken. In order to be able to equally share the load between two bearings on one guide rod, the spindle axis has to be exactly centered between the two linear bearings. Otherwise, yeah, it won't work. But yeah, well, who would position the spindle off center? I mean, this would be kind of stupid. So yeah, that's a dimension I simply omit or will omit in all my calculations. The spindle is dead center between the linear bearings. Yeah, that's it for today. And next time we talk about, and I can't show that here because we're talking about X forces going down to the table. Or let me get the little guy out. This time we will looking at it from the front, and have X forces that is parallel to the X-axis be exerted at, it's giving way, on our spindle. Yeah, and this will lead us inevitably into the third dimension, and up to now we just talked about our upper and lower guide rod or bearing, but when we calculate forces on the X-axis in X direction, we will have to have a look at our spindle. Sorry, at our lead screw, not spindle, lead screw. Yeah, well, see you next time. Bye.